What's up, everybody? Welcome back. Patrick here. Moving on to the next topic in vectors. We're now going to talk about the span of vectors. And this is a common topic that comes up in courses, and it can get pretty weird. And it's pretty tough to explain, but I'm going to do my best. But just as a heads up, you may have to watch this video a couple of times for it to really sink in. And there's probably going to be multiple videos on this topic just because of the amount of information that goes into this concept. And throughout the videos, I'm going to explain this both visually and algebraically in order for all of this to really sink in. Now, you may run into a lot of different definitions for what span of vectors means. The way I like to think about it, it's basically the space created by any linear combination of vectors. And as the video goes on, this definition will become more clear to you. And what we're going to do is we're going to go over cases in both 2D and 3D. So in 2D, that means in r squared, 3D is r cubed. So in r squared, we know all of the coordinates are going to be what? X and Y. So we're just going to be dealing with a normal Cartesian 2D plane like this. And then in r cubed, the coordinates will be X, Y, and Z. So it will be in 3D like this. So this is the Y, this is the X, this is the Z. So let's start off by talking about the R2 case, or the 2D case for the span of vectors. And let's start off with a result here. So what happens in R2 is if you have two vectors, A and B, that are non-collinear, then any vector in R2 can be written as a linear combination of A and B. Right? So here's what this means visually. So if we have two non-collinear vectors, so let's say we have vector A, which looks like this, and let's say vector A is 2 and 3. And then let's say we have vector B here. And let's say vector B is -4 and 1. These are two non-collinear vectors. And what that means is that any vector now in R2, in this whole plane, in the XY plane, can be written as a combination of these two. So another way to say this is that vectors A and B, if they are non-collinear, they span, A and B span all of R2. Right? So this definition and this definition are the same. So if A and B span all of R2, it means that any vector in R2 can be written as a linear combination of A and B. So let's do an example. So let's bring in another vector here. Let's say this here is vector C. And let's say C at its tail has a coordinate of 1 and 6, and then its head has a coordinate at 4 and 7. So notice that these two vectors, they're already in component form, but this vector here, we are just given the coordinates of the endpoints. So what we can do is we can take this vector C and we could put it in component form like this, like these two vectors. Basically, we would take 4 minus 1, which is 3, and then 7 minus 6, which is 1. So vector C is 3 and 1 in component form. So what we can do is, instead of drawing C up here, because it's in component form, this is like the tail is going to start at the origin. So we can take this vector and shift it down here. So let's say this is C, right there. So that's vector C, and now it's in component form 3 and 1, where its tail is at the origin. So this vector, they're both the same. We just took this vector, shifted it down here. So now that we have our vectors here, we can show how this result works. Notice that we have our two non-collinear vectors, vectors A and B, and then we have this random vector C that we brought in. And what we have to do is we have to show that vector C can be written as a linear combination of A and B. Now, what does it mean for it to be written as a linear combination? Well, what it means is we can take vector A and we can multiply it by some kind of scalar, let's say n. And then we can add vector B after we multiply it by a scalar, let's say n, and that will give us vector C. So in this case, m, n are just scalars, some kind of scalars. So this is what they mean by a linear combination. So you can take vector A, multiply it by a scalar, plus take vector B, multiply it by a scalar, and that will give us vector C. In fact, it will give us any vector in R squared, but for now we're just going to work with this vector C here. So let's plug in the component form for all these vectors. So vector A, we know it's 2 and 3. And then vector B, we know it's -4 and 1. And then we know vector C is 3 and 1. So then we can distribute that scalar inside. So we got 2m, 3m, plus -4n, and then 1 times n is just n, equals 3 and 1. So notice we could set up equations here. Notice that 2m minus 4n has to equal 3. So 2m minus 4n has to equal 3. And then 3m plus n has to equal 1. So 3m plus n has to equal 1. So now notice we could solve for m and n using substitution or elimination. We have 2 unknowns and 2 equations. So if we isolate for this n, and then sub in this for that n right there, we'll have 2m minus 4 bracket 1 minus 3m equals 3. So what will happen here? This would go over to the other side, and then this would be 14m, and then we would have 7. So m would be 7 over 14, which would be positive 1/2. And then if we plug in this m value here, we would get an n value of negative 1/2. So that means that if we take 1/2 of vector A and add, or because it's a negative, we would be subtracting 1/2 of vector B, we would end up with this vector C. So how that looks visually, so let me just erase these coordinates here for now, is we're going to take 1/2 of A. Well, notice this is the full A here, so if we take 1/2 of it, that would maybe look, let's say, like maybe up to here. Right, so we just took A and we took half of its magnitude. So this right here is 1/2 A. And then we're going to subtract 1/2 B. Well, notice B is going in this direction, so negative B would go in the opposite direction. So this would be negative B. And then 1/2 of B would be half of that magnitude. Like that. So if we take this vector, shift it up here, then this part here would be minus 1/2 B. So we cut B in half, we cut its magnitude in half, and it's going in the opposite direction because it's negative. So 1/2 A minus 1/2 B gives us vector C. And that was just any random vector that we put in, but we can take any vector in R squared. We can take this vector, we can take this vector, we can take this vector. Any vector in this whole plane in R squared, or R2, we can write it as a linear combination of A and B, but only if A and B are non-collinear. So what that means is that A and B span all of this space because any vector in that space can be written as a linear combination of A and B. Now notice this whole time we've been talking about A and B being 2 non-collinear vectors. But what if they were collinear? Then what would happen? So let's show an example. let's say we have that same vector A, and let's say vector A is 2 and 3. And let's draw another collinear vector to A. So instead of having a non-collinear, let's draw a collinear one. And if you remember, what does collinear vectors mean? Well, what it means is that the vectors are just basically scalar multiples of each other. So we have this vector A. Let's draw another vector B that's collinear. So we got to multiply A by some kind of scalar. We can pick whatever we want. Let's multiply it by -2. So this 2 and 3 would become -4, -6. -4, -6 would be down over here. So let's say this is vector B, -4, -6. Both of these vectors are collinear because they're scalar multiples of each other. So we got vector A, then vector B is in the opposite direction, right? Because we multiplied vector A by a negative number, and it's twice the magnitude because we multiplied it by 2 as well. So both of these vectors are collinear now. And now let's bring in a random vector C again. So let's say C looks like this. Now the question is, can we write C as a linear combination of A and B? And the answer is no, we can't. Because no matter what constants or what scalars we multiply A and B by, they are always going to be on this line here. So we're never going to be able to get to the head of vector C. So we can maybe take vector A, but how would we add vector B to get over here? We can't, because it's going in the same line as A, whether in the same direction or the opposite direction. So collinear vectors do not span R2 because the vectors, other vectors in R2 that are not sort of parallel to that line can't be written as a combination of A and B if they are collinear. So collinear vectors do not span R2. So you may get a question asking, does vectors A, 2 and 3, and B, -4, -6, span R2? Well, you can tell right away they don't because they're scalar multiples of each other, hence they're collinear vectors, so they can't span R2. And it doesn't have to be -4, -6, it could be maybe 6 and 9, right? So that would be like multiplying A by 3. Still scalar multiples of each other, still collinear, they do not span. Now, what if instead of having vector A as 2 and 3, what if we slightly slanted vector A? So instead of 2 and 3, let's say it was 2 and 2.99. Well, now vectors A and B are not collinear. And we can now take vector C and write it as a linear combination of A and B, just from that one slight difference. It's going to be crazy numbers that we would get if you would try to solve this like we did before. Like vector A, you'd have to extend like crazy, and then vector B, you'd have to extend like crazy coming back to get to here. But nevertheless, because they are not collinear anymore, any vector in R2 can be written as a linear combination of them. Again, that M and N that you would get would probably be either very large or very small, but it can be done. So what this means is that you can get a question where they give you two sets of vectors and you can see right away whether it will span R2 or not. So for example, let's say I gave you vectors -5, 3, and then 1 and 2. Would these two vectors span all of R2, meaning that any vector in R2, can it be written as a linear combination of these? Yes, it can, because there is no scalar that would relate these, meaning that these are non-collinear, So these would span R2, right? But what if I have something like, let's say I got -3 and 5, and then I have -21 and 35. What about these two vectors? Do they span R2? Meaning, can any vector in R2 be written as a linear combination of these? No. Because notice that if we take this vector multiplied by a scalar of 7, we would get this vector. So 7 times -3, -21, 7 times 5, 35. So because they are scalar multiples of each other, they're going to be collinear, so any vector can't be written as a linear combination of them. So these do not span R2. So span of vectors in the R2 case and the 2D case, pretty simple. Basically, you got two non-collinear vectors. They span R2. Any vector in R2 can be written as a linear combination of them. If you have two collinear vectors, scalar multiples of each other, then they do not span R2. And now what we're going to do in the next video is we're going to go to the 3D case. It's a little bit more complex because we're now going to be talking about not just the R2, the XY plane, but basically any plane in the 3D space. And we'll cover that in the next section.